Dear ladies and gentlemen, I'm glad to welcome you to my presentation regarding the influence of the energy input on the strength and hardness of welded joints. Within the Aufnahme beginnt in 3, 2, 1. Dear ladies and gentlemen, I'm glad to welcome you to my presentation regarding the influence of the energy input on the strength and hardness of welded joints. Within the upcoming 30 minutes I want to give you a short insight in the development of a new test procedure of weld metals and the result we examined using this new procedure. Afterwards, I want to explain the correlation we found between the cooling time T85 representative for the energy input during the welding process and the tensile strength of welds. And finally, I want to explain the results of our hardness measurements just in a nutshell for you, and I want to have a look on the correlation of the hardness values and the tensile strength of the weld metals. And at the end, I want to summarize all these findings within my conclusions. So, first of all, why do we need to have a new test procedure for weld metals? Usually, we are going to determine the load-bearing capacity of welded joints by using full-scale tests. Of course, we all know these tests are really expensive and time-consuming. On the right side we can see the influencing factors on the weldability of a component, and of course these factors, the material, the production and also the design, are the main influencing factors on the load-bearing capacity of welds too. So therefore we have to cover a huge number of influencing factors to really have a deeper knowledge on the load-bearing capacity of welded joints, and therefore we decided to develop a small-scale test and to use engineering models like we also use them for normal tensile test or for the Sharpie impact test to transfer those results determined with a small-scale test to the component level. And with these small-scale tests we can cover a huge amount on the influence factors out of the material and the production with a simple test method. And this is also one of our design principles. We wanted to have a flat tensile specimen to have a really easy execution of the test. We needed a defined size and geometry of the weld to easily determine the strength and the stresses which are acting within the weld metal. And the failure needed to take place in the weld metal due to the reason that only then we can transfer those results to the component level. Otherwise, when the failure takes place in the base metal, for example, we cannot transfer those results because we just know, okay, our weld metal has a higher strength than base metal, but we do not know the exact strength of our weld metal. And of course, the test specimen should be suitable for different material combinations and production parameters so that we can cover both undermatching welds where the weld metal strength is lower than those of the base metal, but also overmatching welds where the failure usually should take place in the base metal, but as we wanted to determine the weld metal strength, the failure needed to take place in the weld metal. And therefore we decided to use a century-old flat tensile test specimen where we have a defined size and geometry of the weld and also controlled notch factor at the weld seam. So within our experimental test we covered a huge amount on influencing factors. You can see them here. One of the most interesting were of course the material combinations. We have here a table which summarizes the tensile strength mismatchings of the steels we examined. So we have a S500M up to a S960Q with a huge amount on filler metals. Those tensile strength mismatchings highlighted here were the material combinations we have examined within our experimental research, and as you can see we have an undermatching of about 50%, but also overmatchings up to 23%. Furthermore, we examined the influence of the cooling time, the weld preparation, in this specific case the weld opening angle, the number of weld layers, the manufacturing process of the base metal. As you can see, we have both thermomechanical rolled steels as well as quenched and tempered steels, and also the manufacturing process of the welds. Most of our welds were fully mechanized welded, but some of the welds were also welded by hands in construction workshops. So first of all, I want to give you an insight on our experiment on the influence of the base material. What you can see here on the left side are the stress strain curves for all the 4 base metals we examined in combination with filler metal G62 for a cooling time of 12 seconds. And what we can see is that there are no significant differences. Having a closer look on the mechanical properties, we can see that the base material has more or less no influence on the strength properties. We have a scattering within the strength values we were expected, and also on the elongation we have a large reduction in the elongation at fracture, but having a look on the total values, also this reduction is neglectable. So by using these specific test specimen, we could find out that there is no specific influence on the base material on the strength of the weld metal. But what we can see is that there is a huge impact of the cooling time T85 on the mechanical properties. Again, on the left side we have stress strain curves for 3 different cooling times of the material combination S690QL in combination with a G42 for the cooling time of 5 seconds, 12 seconds and 20 seconds. And having again a look on the mechanical properties, we can see that we have a large reduction in the strength and an increase on the ductility of the welds. So the cooling time, of course, is a very important influencing factor on the mechanical properties of welds, which should be covered in all our examinations with the focus of welded joints. So now it's interesting to describe this behavior of the tensile strength with regard to the cooling time T85. What we can see here are all the test results we achieved with these different filler metals, and of course here we can have a look on these results and can describe the correlation of tensile strength and cooling time T85 for each filler metal by its own, but we cannot compare the results in a good way. So therefore we decided to normalize the tensile strength to the cooling time of 12 seconds. Why 12 seconds? Now, as you can see on the left side, this is the field where we have the largest amount of results. And what we can see is that we can describe this behavior with different mathematical functions, with a logarithmic function, with a linear function, and also with a quadratic function. And all of these functions show a more or less good correlation. So within the next step, we decided to compare our results to results from the literature. Again, the normalized tensile strength with regard to a cooling time of 12 seconds. And now, as you can see here, we have a larger spread of the cooling times. These are the results of so-called time temperature transformation examinations, which are from the literature. You can see the source on the right corner, and having a closer look on our time period of the cooling time, we can see that we have again a more or less comparable correlation to our results. So again, you can see them here, and also the regression function is more or less equal. So we can see that the results we achieved are representative for a huge amount of filler metals. Of course, there is at the end a large scattering, especially for short cooling times, which is depending on the different filler metals and their different transformation behavior on the crystallization size. But at the end we have at least found a general function to describe this behavior of the tensile strength and the cooling time in general. So we also performed hardness measurements here in 2 layers. Layer 1 is the upper layer, layer 2 the lower layer, to have more information about the weld cross section at the end. And what we can see is that we have interesting points where we also can examine the influence of the upcoming weld layers. I have shown some microsections here for you. The frames are representative, or the colors of the frames are representative for the positions you can see on the left picture, and we have different microstructures and therefore of course different hardness. And so what we can see is that it's not homogeneous, our microstructure, but we have large differences and also therefore large differences within our hardness. But there is a Eurocode, the EN ISO 1800-265, and this code gives us the opportunity to have a correlation of the hardness value and the tensile strength of the weld. And we examine this. We use the mean values of the integral hardness values, so all hardness values over the cross section were used, and we also take into account the standard deviation of our hardness values. So, and what we can see is that we have a large scattering and that there's not such a good correlation with our test results. So therefore we decided to have a closer look and just take into account the hardness values which were in the failure area of the weld. But what we can see here is also that there is not a good correlation at the end. And within this code there's also mentions that you need to take into account a specific standard deviation of about 85 Newton per square millimeter for the test results, and therefore they are usually not useful for our design formulas we have, because just to this large scattering we get really conservative tensile strength to use for. So therefore the test procedure we developed is a good alternative to determine the mechanical properties of welds in a good way. And this is also one of our main findings. We were able to determine the mechanical properties of weld metal experimentally, and we found out that the weld metal properties are mainly influenced by the filler metal and the cooling time T85. All other influencing factors were more or less neglectable. We found a functional description of the weld metal properties as a function of the cooling time T85, which shows a really good agreement with our expected values. So we have the opportunity to expand the field of the cooling times we have covered within our experimental research to have a deeper knowledge on the behavior of our material properties. And finally we found that these converted hardness values cannot replace experimental determination of the mechanical properties of weld materials. So therefore I want to thank all our project partners and thank you very much for your attention. I hope you have a nice conference, and if you have questions, please feel free to ask me.